Hello, my name is Farshad Taeb, 219-175-355, and welcome to my Civil 4022 Water Resources Engineering Final. To start off, we have the first question, which is the design of the channel lining. And essentially what we have is that there's a damaged concrete line trapezoidal channel that needs new lining, and we have to choose new linings that will improve the performance of the channel against shear stress. Below we have some of the givens and some of the assumptions based off the question. So following the allowable shear stress method, the first thing we would do is we would find the geometrical characteristics of the channel. After so, we would find the average shear stress across the channel, and from there we would find the allowable shear stress of different material linings, which we would use to compare with the average shear stress across the channel to see which material would be the best fit for our design. What was not given to us in this question was the bottom width of the channel. In order to find that, we use Manning's formula for flow capacity with the givens of 1500 meters cubed per second flow, 0.013 Manning coefficient for concrete retrieved from table 21 of the City of Toronto's criteria for design document, as well as the channel slope of 0.015 meters per meters and the side bank slope of 1.7 horizontal per vertical, and the channel flow depth of 3 meters. Plugging these values into our equation, we find that the bottom width of the channel is 79.8 meters, and the hydraulic radius of the channel is 2.78 meters. After finding the geometric characteristics of the channel, we can present a schematic of the channel shown below. Next, we have to find the average shear stress and the max base and side shear stresses. To find the average shear stress, we use the formula, which is specific weight of the water multiplied by the hydraulic radius multiplied by the slope of the channel. Plugging these values into the equation, we find that the average shear stress of the channel is 40.9 newtons per meter squared. To find the max base shear stress, we use a similar procedure, but instead of the hydraulic radius, we use the flow depth of the channel. And the value we would find for that would be 44.145 newtons per meter squared. And to find the maximum side shear stress, we would find a coefficient to multiply by the max base shear stress. And to find this coefficient, it relies on the side bank slope. So if your side bank slope is between the values of 1.5 to 5, we would use the equation 0.066 multiplied by the side slope plus 0.67. And the value for this coefficient we find is 0.7822, and we multiply that by the max base shear stress to find the max side shear stress of 34.53 newtons per meter squared. So here we chose 3 different material lining designs and their allowable shear stresses. Comparing these 3 with the average shear stress that we found in the previous slide, we can see that rock riprap D50 equaling to 150 millimeter is the best option out of the chosen 3, and this is because that rock riprap D50 150 millimeter has a comfortable shear strength of 95.8 newtons per meter squared, which can comfortably handle the 40.9 average shear stress we found. Rock riprap provides great protection against erosion. It is fairly easy to install, and comparing the 150 millimeter to the 300 millimeter, the 150 is more cost efficient, and overall there's very little maintenance required for this material. In the next question, we have to use the rational method to determine the time of concentration, peak rainfall intensity, and peak runoff of a 2-year rainstorm. The givens of this question was that we have a catchment area of 20 hectometers. This area is a single family residential area, and the slope of the catchment is at 0.0075 meter per meter, and the length of the catchment is at 400 meters. So the way we go about this question is that we have to find the appropriate formula for time concentration first from the runoff coefficient. After finding the time concentration, we can use that to find the peak rainfall intensity from the designated IDF curve chart or the formula. After finding the peak rainfall intensity, we can use that to find the peak runoff, and from there we would move on to finding the maximum flow of a pipe, and we would calculate the 100-year rainstorm event peak flow and find the conveyance factor. The first thing we do is we find the runoff coefficient from table 21 of the City of Toronto's criteria for design. We find that for a single family residential area, we have a runoff coefficient of 0.65. Since 0.65 is larger than 0.4, we have to use Bransby-Williams formula, shown below, which we find the TC value of 17.9 minutes, or 0.298 hours. Plugging this value into the peak rainfall intensity equation, we find for a 2-year rainstorm, we find that the intensity is at 56 millimeters per hour. And plugging this intensity into the rational method equation, we find that the flow of this catchment is at 2023.84 liters per second, or 2.023 meters cubed per second. Next up, we're given the specifications of a 750 millimeter pipe, and to find the max flow capacity of this pipe, we would also use the Manning formula once again with the new set of givens shown on the left, and we would find that the max flow capacity of this pipe is at 1.113 meters cubed per second, and the velocity within this pipe, within this full pipe, is at 2.519 meters per second. To find the 100-year peak, we follow the same procedure as a 2-year peak, and we would plug in the 100-year peak values of A and C this time. We find that the intensity is at 157.25 millimeters per hour, and we would plug this back into the rational method formula to find the catchment flow of 5.683 meters cubed per second. And the fraction of the storm water conveyed by the pipe is basically the flow capacity of the pipe over the flow of the 100-year rain event. And we find that this fraction is 19.6%. The third question here we have is a cost benefit of the low impact development. And what happens here is basically to reduce the volume of excess stormwater runoff in York University, and to also improve the water quality. 2 infiltration basins are proposed, and we have to determine the net present value of the project with different adjustments. So given in this table below, we have a project life of 20 years, a discount rate of 4%, 2 basins. Each surface area of each basin is 125 square meters. A unit capital cost of the basin at $800 per square meter, and this is a one-time cost. A unit operational and maintenance cost of the basin, which is at $10 per square meters per year, which is an annual cost. We have the groundwater recharge benefit at $800 per year, and this is an annual benefit. And we have the averted cost of the stormwater pipes and inlets at $310,000, and this is a one-time benefit. Finally, we have the pollution fee of $300 per year, which is an annual cost. So how we go about this is we have to determine the upfront costs and benefits of the project, and we sum up the total annual cost and the total annual benefits of the project as well, and we apply the costs and the benefits over a discount factor raised to the power of each year past, and all in all we subtract the cost from the benefits and we find our cost benefit. Here we find the initial capital cost and the initial averted costs. So for the capital cost, we have $200,000 price for the project, and the averted cost is $310,000, which would give us a net positive of $110,000. The annual cost of the operation and maintenance plus the pollution fee will come out to $2,800 per year, and the annual benefits of the groundwater recharge would be at $800 per year. To find the present value of the benefits, we take the $800 over 1 plus the discount factor raised to the power of time, and similarly for present value costs we would take 2,800 over the 1 plus the discount factor of 4 over the power of time, the raised to the power of time. And all in all, after 20 years of the project life, we see that the cost benefit analysis is at a net positive of $82,819. So here we have an adjustment to the pollution fee from $300 to $500, and this raises the annual cost from $2,800 per year to $3,000 per year. And here we can see that the net present value changes to $80,101. So here we have the adjustment of 25% reduction to the surface area and a 5% increase to the operation and maintenance costs. The surface area comes down to be 93.75 square meters, and this reduction in surface area results in the reduction of capital costs from $200,000 originally to $150,000, and the annual cost of operation and maintenance from $2,800 to $2,268.75. These reductions in the cost significantly raises the net present value of the project after 20 years from $82,000 to $140,000, which would mean that these changes are very beneficial to make to the original proposed design. Here in the appendix, I have the runoff coefficient table 21 from City of Toronto's criteria for design, as well as the Manning end value table 22. And we have the rainfall intensity curves for City of Toronto as well, and the Bransby-Williams formula, and all of which was used throughout the conduction of this final. Presented below are my reference lists. And something that was interesting to me throughout this course was how there is a lack of water quality monitoring within the conveyance system, which essentially means that once the treated water leaves the plant, there isn't a lot of monitoring, and we don't really know exactly what is going on within those pipes, but we have several complex models that we can use to have a better understanding of what's going on and use that for our designs.